Okay, so for sequences, let me first define a sequence for you. So sequence, you can write this sentence. A sequence is a function whose domain is all positive integers. Okay, so what I'm saying is 1, 2, 3, 4, the counting numbers, positive integers. Okay, so the positive integers are literally 1, 2, 3, 4, etc. Also known as the counting numbers. Also known as the natural numbers. But I am saying that a sequence is a function. Okay, so sequences in math can be drawn, they can be written, or they can be expressly stated as a rule. So let me show you those three representations real quick, okay? For example, we usually don't write f of x, we would write a sub n. So maybe you'll see something like this, you know. What do you do with this thing? Well, you should know that because it's an n, it's most likely a sequence, okay? So there are lots of things we can do with this sequence. We can plot this sequence, we can list this sequence, or we can just study it and study its properties. But it is a list of numbers. The first thing you might want to do is just sort of expand it out. So what we were saying is that you're supposed to be using n equals 1, n equals 2, n equals 3, n equals 4. Don't plug anything else in. Only counting numbers, please. So if you plug in counting numbers, you would get 1 plus 1 over 1 plus 2. 2 plus 1 over 2 plus 2. 3 plus 1 over 3 plus 2, and so forth. 4 plus 1 over 4 plus 2, and you can do as many as you like, at least 3, I guess. So this just basically comes out to be 2/3, 3/4, 4/5, 5/6, 6/7, and you could probably guess the next one is 7/8, right? So kind of a nifty little pattern there. But that's the first thing you can do with sequence. You can just sort of expand it out. These are really the same thing, these two greens. Okay? The first one is called an explicit rule, nth term, general term. There's lots of names for it. Let's title it. So this guy right here is sometimes called the general term. Some people call it general term formula. Some people call it general term. Some people call it the nth term or nth term formula. Some people call it the explicit rule. There's a lot of names for that thing. Later it might get called the summand. We'll see later. Okay. This over here is just the sequence. And these are all called elements. Kind of like in a matrix, you have the elements, right? Was this hard to create? Not really. I just plugged in 1, 2, 3, 4, and 5. How come I didn't plug in 1.5? Yeah, the domain won't allow it. I'm not allowed to plug in 1.5. Okay? I could actually plot this. Now you notice the y values aren't very interesting. Actually, the y values, the outputs are all very small fractions. The biggest I ever got here is 6/7. That's not very big. But the n, the domain is 1, 2, 3, 4, 5. So let's go ahead and label our x-axis 1, 2, 3, 4, 5. And this is actually the n-axis, technically, not the x-axis. But for the y, let's just put 1.0 here. Maybe 0.5 goes there. Okay, so as we go through to plot these, you might want to think in decimals. But the first term, that means n is 1, is 2/3. So that's about 0.6, almost 0.7. The second term is 3/4, is 0.75. The third one is 4/5, that's 0.8. I'm sure yours looks better than mine. The fourth one is 5/6, which is like 0.8 something. And the last one is 6/7. This is getting very, very close to 1. And it's extremely tempting to connect the dots. But I can't connect the dots because when you connect the dots, you are passing through the points between these which aren't in the domain. So this is what we call a discrete function. Is it continuous? No. Where are the discontinuities? Pretty much everywhere. This thing is completely broken. It is just made up of select points. Okay? Now I could draw more of them, but I cannot draw any between these. Okay? And another thing I'm not allowed to do is I'm not allowed to draw a Y-intercept. Even though you can physically plug 0 into here and get 1/2, you're not allowed to, because 0 is not a counting number. I mean, who looks out at an empty pasture, out in an open field that says, 0 cows? That's not a counting number. Right? You look out there, you see one lonely cow, the first thing that comes to mind is 1 cow. If you look at an empty field, the first thing that comes to mind is not, 0 cows. Right? So that's not a natural way to think. If you think that way, maybe you just really like cows, you're hoping to see one. All right, but we start with 1. That means there's no Y-intercept, although you could get an X-intercept sometimes. If you plug in, n equals 20 in a certain function, you might get an X-intercept, but you'll never get a Y-intercept here, really. Okay, so this is very much like f of x equals x plus 1 over x plus 2. Okay, so let me just kind of show you the difference between them. Okay, so down below we'll draw f of x equals x plus 1 over x plus 2. That is not the pen I was hoping for. I would rather have a real pen, thank you. So this is kind of like f of x equals x plus 1 over x plus 2, which we've been graphing all year long, right? So x plus 1 over x plus 2 actually looks like this. Has a vertical asymptote here, horizontal asymptote here, has a y-intercept of half, x-intercept -1. I've drawn this 3 times today, so that's why I'm going quickly. This is a little bit different, isn't it? Not quite the same thing. If you wanted to compare the sequence graph and the function of all real numbers domain graph, well, I guess you could kind of say that your dots are right here, living on the red curve, but they're only part of the red curve. Okay? All right. So we still have a function, it still has a domain, right? It still has output, it still has range, right? It still has a graph. But we don't call them functions anymore, we call them sequences. And we don't connect the dots at all. Okay, so there's 3 ways right there for you to sort of display a sequence. What are they? We have an explicit rule. We have an actual sequence where you list out the elements, or you can graph it, but don't connect the dots, right? So you have 3 ways to represent your graph, or your sequence. All right? Now let's take away the best part of all that and make it harder. Now I'm going to just give you a list of numbers. Now this is a representation of a sequence. It's one of the 3 representations. The problem is we were not given the explicit rule. The explicit rule is nice to have because the explicit rule will help us to find other terms that aren't listed. For example, what if you wanted the 900th number in this list? Would you be able to find it? You probably could figure it out. But you wouldn't want to write out the first 899 numbers. Nobody wants to do that. Wouldn't you rather just have a little rule that you could plug 900 into? Or if you want to find the 10th term even, maybe you're too lazy to list the rest of should be an explicit rule for this, you see, and we like to guess at and find what it is. So typically what I do on these, I'll just look at the sequence, and before doing anything, I'll write down that this is the n equals 1 term, this is the n equals 2 term, this is the n equals 3 term, this is the n equals 4 term, and I'll try to find a connection between the red and the black. Okay? So 1, what does that anything to do with 2? And what does 2 have to do with 4? And what does 3 have to do with 6? And what in the world does 4 have to do with 8? Is there a connection between 1, 2, 3, 4, and 2, 4, 6, 8?
Yeah.
Okay, so they're double, right? The black numerators are double, twice as large as the red numbers, right? So in a very real sense, this top is just simply 2n. Okay, and now you can ask yourself, well, how do the denominators, 3, 5, 7, 9, how does 3, 5, 7, 9 relate to 1, 2, 3, 4? Or you can ask, what do the bottom black numbers have to do with the top black numbers? What do you notice about the bottom black numbers? Compared to the top. You don't have to compare it to the red, compare it to the top. 1 more. It's always 1 more. So if the top is 2n, the bottom then would automatically be 2n plus 1. Now if you're not sure you constructed the explicit rule correctly, you can easily test it by plugging in 1, 2, 3, and 4 to see if it regenerates 2/3, 4/5, 6 7s, and 8 9s. Does it work when I plug in n equals 4?
Yes.
2 times 4, 2 times 4 plus 1, 8 9s. Check, it works, right? Okay, so this is a very, very easy one, but actually it teaches us a lot. It teaches us that even numbers can be generated using a 2n. 2n generates 2, 4, 6, 8. Who do we appreciate? Evens. Okay? 2n plus 1 generates what kinds of numbers? Odd numbers, correct. So 2n plus 1, 2n generates evens, specifically 2, 4, 6, 8. And 2n plus 1 generates odds. Unfortunately, it starts at 3, 5, 7, 9. Does anyone know how we could get our odds to start at 1, 3, 5, 7? Maybe we shouldn't use 2n plus 1, 2n minus 1. 2n minus 1 will generate odds starting at 1, 3, 5, 7. These are just little clues that you're going to need later, okay? So keep these in a box on your paper because there are plenty more of them. Let's try another one. How about this pattern? Give me a second. Okay, I got it. 2 over 2. You might say, Mr. Sir, why don't you just reduce it? Because then it would be harder for you. Okay? 2 over 2. 4 over 5. If you see the pattern, don't shout it out, okay? 8 over 10. You might say, those are the same thing, second, third term. I agree. 16 over 17. 32 over 26. Ooh, now it's getting harder. Your job is to create a formula. It doesn't have to be called A sub n, we can call it B sub n this time. Create an explicit formula or explicit rule, something that could generate the 99th number in a heartbeat. How would you do it? This is a different pattern, isn't it, from before? What did I tell you that I usually do before I start a problem? I label this n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. The reason I do this is because now I'm not trying to figure out necessarily how 2 relates. Like, you don't have to compare the top and bottom, you know, but rather you have a third reference point. 1, 2, 3, 4, 5 have anything to do with 2, 4, 8, 16, 32. Right? So maybe we don't even need to worry about the bottom right now. 2, 4, 8, 16, 32. Where did we see these numbers before? Okay, I'm going to give you a couple minutes to think about this. Ask yourself, are there other ways to write 2, 4, 8, 16, 32? Can you think of another way to write 32, for example? 32, the number 32. Can you think of another way to write it? Factor down or whatever. So, okay. Let me pause the video and you guys can play around with this one. I'm trying to create an explicit rule. So Eddie's saying, he's saying that the top is 2 to the n. Does that work? 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16. 2 to the fifth is 32. Good job. Okay, the bottom's different though. Anyone figure out the denominator? What'd you put, Blake?
N squared plus 1.
N squared plus 1. How did you come up with that?
I just compared it to the top.
Okay, if you look back above, you'll realize that in the previous problem, I had used... Wait, you compared it to the top. What do you mean you compared it to the top? You compared it to the top? The top is 2 to the n.
I just plugged in
Okay.
I got a solution.
Are you sure yours works?
Yeah. Yes.
Yeah, it does work. Okay, so this is kind of hard to see, but basically none of these numbers are perfect squares. None of these numbers are perfect squares, but they're all one larger than a perfect square. So for example, if you took away 1 from each of these, it would be the list 1, 4, 9, 16, 25. Does that list look familiar? Sure it does. That's just the perfect squares, right? Okay, so you feel you got a little lucky on that? No. Okay. Let me show you something interesting about the denominator here.
35, 79.
Yes. You'll notice that on the bottom, this is growing by 3, then it goes up by 5, and then it goes up by 7, and then it goes up by 9. Do you think it's a coincidence that we got 3, 5, 7, 9 here? No, so listen carefully. I just want to say this before you go. Okay, there's a couple takeaways here for today. Back on the first problem, we saw that 2n, see this 2? That 2 creates a 2 jump. See how it goes up by 2's? Whether it's odd or even, they both have the 2 in, which creates a 2 jump. It's kind of like mx plus b, you know? That's like your m. That's your rise. This 2 here causes jumping by 2's. But when your list is jumping by a jumping amount, that's quadratic. So if your rises are a linear function, when your rise is actually rising, it's very likely it's a quadratic or a cubic. And the top was a little more obvious. But that's the answer. Good job. You'll have one of these on the board Thursday when you walk in. See if you can figure it out.